Okay, let's continue watching. I was gonna watch her, but maybe we should first finish watching her.
With bombs for whatever reason. And these bombs are photon sensitive or light sensitive, which means that if you shine a light or even a single photon at one of them, they will detonate and explode. But the problem is that some of these bombs are duds. Is there a way to test whether a bomb is live without detonating it? Quantum physics says there is. These two guys with really cool names, Avshalom Ilitsa and Lev Vaidman, came up with a thought experiment to solve this problem using what they called an interaction-free measurement, meaning that they could test whether a bomb was live without an explosion. To understand this, we need to talk a little bit about something called quantum superposition. Quantum superposition is the theory that an
So I think I already said it does not exist, in my opinion.
object exists in all possible states
That's nonsense.
at the same time,
No, it doesn't.
and the act of measuring that object
No, no. It's just that you don't know, and then you do know. Nothing to do with reality, just your knowledge. Reality, nothing changes because you know something.
forces it to choose one state.
No, choose it has intelligence. That's nonsense.
So there's a very famous thought experiment about this called Schrodinger's cat.
Yeah, that's not a thought experiment. It was meant to be a joke.
In a box, there is a cat, a vial
Schrodinger wanted to show that it makes no sense.
of poison, a hammer, a Geiger counter, and some radioactive material. When the radioactive material decays, the Geiger counter detects it, triggers the hammer to smash the vial, and kills the cat. The thing is, we don't know when the radioactive material will decay. It's completely random.
Wait, I didn't check the audio. 1 second. Oh, shoot. The audio. The audio. Let me check the audio. Ugh. The audio. It looks good. Let me check on my iPhone. 1 second. Check. Check it. Check it. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Yeah, it sounds good. Let me just maybe. I don't. I'm not gonna put the link. No one joins me anyway, so I'm all alone.
So if we were to guess at any moment in time, would the cat be alive or dead? Surely it must be one or the other, right? Well, according to quantum physics, the cat exists in a superposition
What does it mean according to quantum physics? According to your understanding of the universe.
of being both alive
According to your understanding of the universe, a cat can be dead and alive. Okay.
and dead.
You should commit yourself to a mental asylum. Have a great rest of your life.
Remember, it exists
And this is what most people in the world believe.
in all possible states until it is measured or observed.
Yeah, this is what everyone believes. Unbelievable. They believe quantum physics dictates this utter nonsense.
It is only when we open the box and take a look that the cat has to choose a state. Today, it chooses to be alive. Okay, so a cat can't exist in a state of quantum superposition.
Oh, wait a minute. You just said that the cat is, and now you say that it can't. Well, then you just contradicted yourself. Okay, you need to decide whether you want to commit yourself to a mental asylum. You honestly do. You need to decide. It's up to you because you're saying two things that are completely contradictory. A couple of seconds ago, you said the cat is both dead and alive until we measure. And now you're saying, well, a cat can't be both dead and alive. Oh, but just a second ago, you said she can. It can. So you need to decide. Obviously, it's utter nonsense. Obviously, you disagree with it. That's exactly what Schrodinger was aiming at. He wanted you to commit, and you're not committing. That's it. Schrodinger won. Have a great rest of your life. There's nothing else we need to say. That's it. That's exactly Schrodinger's point. You can't say the cat is both dead and alive. Good. Therefore, you cannot say the particle decayed and not decayed because these two things come together. So if you're going to tell me that there's quantum superposition, you have to agree that there is a cat superposition. You cannot separate the two. If you're separating the two, then congratulations. You're a lunatic. You can't separate them. How can okay, anyway, this is a waste of time.
Position because it's not a quantum object.
What do you mean it's not a quantum object? But the cat's life depends on a quantum object. That's exactly Schrodinger's thought experiment. That's exactly it. He wanted you to commit. He connected a quantum object to a cat. And now the cat is in superposition. So if according to you, superposition exists, then the cat is in superposition. You have to, he's forcing you to commit. He's taking the quantum nonsense superposition and he's forcing you to admit it doesn't exist because you know cats don't exist and not exist or die, living and dying, alive and dead at the same time. That's exactly what he wanted to do. So if you admit the cat is not in superposition, then you're forced to admit that the quantum object is not. You cannot separate the two. That's exactly that. The vial is controlled by the hammer that's controlled by the Geiger that's controlled by the decay. That's it. There's nothing. You cannot escape. Schrodinger doesn't let you escape. You're not going to escape this. You can't just, the cat is allowed, the cat is going to be either dead or alive. Yeah, the cat. But the decay, the quantum object, no, the quantum is a superposition. No, you can't. You can't. There's a chain reaction. The Geiger counter connects the decay of a quantum object with the macro universe. And that's it. You're done. You cannot escape this.
But let's take a look at another experiment which uses...
Wait, what? So you must agree, you're forced to agree that there is no superposition. You're forced to agree.
This is something called a Mach-Zehnder interferometer. A Mach-Zehnder interferometer consists of a light source, a beam splitter, two mirrors, another beam splitter, and two light detectors. The light source emits a beam of light and the beam splitter splits the beam exactly 50-50. The mirrors guide the light toward the second beam splitter, where the two beams recombine and interfere. Now the setup is configured so that the beams constructively interfere on detector A and destructively interfere on detector B. I have an entire video which goes more into constructive and destructive interference called the double slit experiment, which I've linked in the description below.
The double slit experiment is where you teach interference? No, interference you should teach separately about interference of waves. You should start with water waves and go to light. That's interference. It has nothing to do with the double slit experiment. Then you can go also to the double slit experiment.
But all you really need to know here is that when the beams interfere at the second beam splitter, all of the light will show up on detector A. Detector B is left completely dark. So
okay, that's the design of the experiment. Okay.
Because of the way the setup is configured, 100% of the light shows up on detector A. Cool. But what would happen if we slowed the light beam down? Slowed it down so much that it only emitted a single photon at a time. This is where things get a bit weird.
No, nothing gets weird. Either you understand or you don't understand. If you understand, then explain it. And if you don't understand, then get back to work until you understand. As long as you don't understand, you have nothing to say. You can just keep saying you don't understand. Nothing is weird. Okay, so you agree we discovered that all elementary particles are waves. So why are you drawing a particle? One second. I have an email, I think. Okay. Okay, that's not interesting. Everything is is fine. What about this? Okay, everything is fine. Everything is fine. Okay, so we agreed that elementary particles are not particles; they are waves. They should actually change the name of what do you call it? The elementary table. The theory of whatever. Anyway, it's quantum field theory. So everything is a wave in the quantum field. So there's no such thing as this bullet. It's always a wave. So an electron, right? So yesterday we discussed what a photon is. Let's go over that quickly. What is a photon? So we drew a diagram, and I think I ended up having to run away in the middle of the discussion. 1 second. Yeah. This one? No. This one? No. This one? Okay, this one. Ugh. This one. They changed the thing. They changed the thing. Okay. We don't need this for now. So what is a photon? Okay. So this is very important. This is a discovery that I made just yesterday. Come on. This is a fresh discovery. Okay. So what is a photon? So a photon. So the story goes, if you listen to the experts, so they'll tell you that when an electron drops from a high energy level to a low energy level, it releases a photon. It's as if the photon was trapped inside the belly of the electron. The electron was full of it ate a big lunch, so it had a photon inside its belly, and then when it went down from a high energy level to a low energy level, it let go. It pooped the photon. That's what you would understand from the experts. So that's no, that doesn't make any sense. That contradicts. That doesn't make any sense. Anyway, so what does happen? So what does happen is, for some reason, let's say we had an electron, and we were able to get the electron excited, so it went over to this energy level. We heated up the hydrogen electron. We shook it. We vibrated it. We excited the hydrogen atom. We shook it. So the electron ended up at a higher energy level. Then the electron at a high energy level is unstable. It is more stable for this electron to drop to its lowest energy level. So it drops. Now, when the electron drops from high energy to low energy, it bumps against this wall, the lowest energy wall. And as it smacks its head against that smack is basically that's like clapping your hands. It smacks against it and vibrates, causes a vibration in the ether, what is also known as the quantum field. And that is a wave. Now, all waves, if I ask you any wave you see, is it a finite wave or is it an infinite wave? Are there any infinite waves? I'll ask you a question. Have you ever seen an infinite wave? And the answer should be no. You've never seen an infinite wave. You went to the ocean, you saw waves. Were these waves infinite or were they finite? Your answer should be, well, obviously all waves are finite because they're all limited to Earth and to the ocean and so on. So they're all limited. Then my response is, well, that means they are quantum. Those are quantum waves. not exactly quantum, but sort of quantum. They're not infinite, so they're quantum. They're quantified. They are of a certain quantity. Now, a photon is the minimum quantity. You cannot split a photon in two. You cannot have two half photons. So the way nature works, the way the ether works, somehow, is that a photon is limited. It's limited to I guess to a time and space, just like any other wave. But it cannot be split into. The difference between a photon and any other wave you've ever seen, they're identical in terms of being waves, except for a photon cannot be split into, whereas a wave in the ocean you could theoretically split in two and nothing, you don't have to recombine them. But a photon you cannot split into. That's the way I see it. But it's a wave. I see we have two people watching us right now, which is very nice. You know what? Let me put the link. So if you want to join us, you don't have to ask me. You can just join. There you go. Okay. So that is a photon. So when a photon comes out of this smack, it has, I would say, an actual direction, an actual momentum, maybe even they say it has a spin, so it has an actual spin. It has these properties. It doesn't have a mass. It's massless. Which means, all that means is that it does not interact with the ether to produce inertia. So usually the way the ether interacts with other waves, with other particles, particle waves, is that the ether annihilates against when it interacts with massive objects, such as a quark or even an electron. When the ether interacts with an electron, the ether annihilates a little bit. And this annihilation, we feel it as, I didn't do that, that's a glitch. We feel it, this annihilation, we feel as inertia. That is what we somehow we feel it as inertia. And this is the Higgs mechanism. This is not me. Well, Higgs didn't say that the ether annihilates. He just said that the quantum field, the Higgs field, or the Higgs mechanism of the quantum field causes the electron to bounce back and forth. And this causes the electron to switch its chilarity or something. It spins back and forth. It changes its spin. Where the photon doesn't change its spin. So the photon doesn't interact with the Higgs mechanism. So the photon is not perceived to have a mass. This mass is just the bouncing back and forth of the electron with the Higgs mechanism. This bouncing back and forth is what we perceive as a slowdown, and that's what we perceive as inertia and mass. That's all it is. Whereas a photon, it doesn't interact with the Higgs mechanism. It doesn't bounce back and forth, so it just moves normally, which is at the speed of light. It's just the normal progression, the normal propagation of energy in the ether, which is just a bunch of objects, a bunch of particles. These are the ether particles. I'm assuming there's only one type of particle in the ether, and there's some interconnectivity between the ether particles. But I don't know anything about the ether. I honestly don't, and I don't know how we can find out anything except for, that's for a different lecture. So that's all that a photon is. So it's just a wave. It has a direction. It cannot spread. So we're used to waves spreading. We're used to waves going in all directions at the same time. But that's not what a photon is. That's just not the nature of this creature. For some reason, it doesn't spread. I don't know how it does that. So that means it is a Fourier series of waves. It's not just one wave. There's multiple waves that create what looks like an object. It looks like an object because really it's a bunch of waves of different wavelengths. It's a combination with different amplitudes, just like Fourier explained. And now no one is watching. It's okay. Anyway, so this photon, and that's it. That's a photon. So it's always a wave. It's a wave. That's it. It's a wave with it's a Fourier wave, which means it has the properties, some of the properties of an object. It seems to be limited in scope, in direction, in momentum, in space, in position. Just, it's just a Fourier. Right? We can produce this, or we can reproduce this. This is reproducible in real life, in our macro universe. We can reproduce this. I think I can reproduce this. I don't know. A little bit. Not exactly. But as I said yesterday, the more I look into the quantum world, the more it looks like the macro world, and I don't see the distinction. It's just waves in the ether, and it's just wave mechanics. That's all it is. And that's not just me saying it. I mean, other people have noticed it, obviously. Dialect noticed it. And what was the other guy's name? I need to remember. There's another guy who teaches special relativity. And he also agrees with some of this. Okay. But he doesn't like ether. He says there's a problem, some mathematical problem with ether. It's fine. Okay, so that's a wave. Let's get back to up and atom. So this is incorrect. It's a wave. So a wave leaves the right. So there's an electron here that fell from a high energy level to a low energy level. It smacked against the lowest energy level. And a wavelet, a photon wave came out of that. So a photon wave came out of that and it's going in this direction. And it's a wave. And as a wave, this is a perforated mirror. So it's a beam splitter. So a photon can go as a wave. It can go in this direction and this direction simultaneously, which is, I agree, I don't understand it. So it looks weird because it's supposed to not be able to do that. So I don't know how it does that. It goes both in this direction, hits this mirror, goes in this direction, and again gets to the beam splitter. And from here it goes this way and hits this mirror and hits this beam splitter. And this happens at the same time. So it's a wave at this point. So the wave is recombining with itself, which we've seen already in the double slit experiment with photons and electrons. And they set it up such that it completely shows up here and it does not show up here. Now, theoretically, they could show up in both places. Couldn't they? That's the question. What if they force it to show up in both places? I don't know how they can force a single electron to do a single photon to do that. I don't know how you release a single photon. I'm always worried about people that tell me that they released a single photon. How do you know a single photon was traveling? How do you know? I don't know how you would know that. Honestly, I just don't know. So I don't know how you measure this. And everything you tell me, I don't know. I don't know the legitimacy of this story. Now, if you do this with an electron, I can more readily believe that you're releasing a single electron. But I would have the same questions. How do we know that a single electron was released and not multiple electrons? So that's a good question. I don't know. Let's check the audio. So that's a good question. I don't know. Let's check the audio. Okay, the audio sounds okay. Okay. Anyway, let's check this notification. No, nothing interesting. Anyway, so the single photon went this way and this way, which is weird. But then it recombined here and shows up only here and not here. Weird. Okay. I mean, not weird. As long as it shows up only here and not here, I guess it's fine. If it. Let's see what she says.
Expect that 50% of the time the photon showed up on detector A and 50% of the time it showed up on detector B. I mean, I know we said that the light beams interfere constructively on A, but you need two objects to interfere with each other. So in the case of a single photon, it should show up on both detectors. But the results showed that 100% of the time the photon showed up on detector A. Not a single photon was detected on B.
So we already know that a photon does interfere with itself because it splits. It goes through two slits at the same time, which does seem weird. Meaning it doesn't make sense that an object that we defined is the minimal and cannot be split in two, splits in two. So something is wrong with our assumption. If we say that something that we decided cannot split in two seems to split in two, well, we have to make up our mind. So why did we decide that it cannot split in two? So Planck had to say this because of the UV catastrophe. He said that he needed a minimal energy level. Otherwise, he would get infinite energy. I don't know. I never understood the UV catastrophe. I never understood it. So I don't know. And I never understood. I don't understand it. I don't understand it.
So what's going on? The photon interferes with itself?
I mean, we need to decide. If a photon can interfere with itself, then it's able to split. It's able to go. If it's able to go through two slits at the same time, then it's not a single entity. Then a photon is allowed to split in two, and every elementary particle is allowed to split in two. But then, what's an elementary particle? So you can have half an electron. How? So why do we have electrons in the universe? Why not half electrons or a quarter or a millionth? Why are there electrons in the universe? Why aren't there double electrons. So I don't know.
So the photon takes both paths and interferes with itself at the.
I mean, if you draw it like a particle, yeah, that's completely nonsensical. But if you draw it as a wave, it makes sense. I'm just thinking, how can a wave, as a wave, we decided it's a type of wave that cannot split in two. It's a minimal wave. This is the minimal wave, the minimal wave. But even according to Fourier, it's not a minimal wave. It's a combination of many waves. So it's not a single wave. Even Fourier agrees that there are many waves involved. I don't know.
The second beam splitter. Now I know what you're thinking. Aren't the detectors a form of measurement? Well, notice the detectors only really measure what happens to the photon after it hits the second beam splitter. If the photon takes the lower path, there is a 50-50 chance it will end up on either detector A or B. And if the photon takes the upper path, there is still a 50-50 chance it will end up on detector A or B. So the detectors actually tell us nothing about which path the photon took. This not knowing is what allows the photon to undergo quantum superposition.
No, that's nonsense. That's obviously nonsense. This not knowing has nothing to do with it, cannot have anything to do with it. That doesn't make any sense. How does it know that we don't know? You could say if it does not interact, it behaves like a wave. But if it behaves like a wave, then it's split in two. It couldn't know that it's going to be recombined. So if it splits in two, we lost it. We lost the photon. So either we had two photons to begin with, or many photons to begin with. How do you know it's a single photon?
Position, existing in both possible states and taking both paths. I know it sounds crazy, but
I don't know anything about these experiments. They never show us these experiments. They always show us this nonsense. But that's not true either. They do show us sometimes the setup. So I don't know. But I'd like her to take time, set up the experiment, show us the experiment.
this happens. So how can we use this weird phenomena to test bombs? Well, let's first place a dud bomb in the lower path. Now let's see what happens if
Okay, I mean, she's going down a path that makes no sense. So she's going to keep getting more and more nonsensical.
the photon takes the upper path. A 50-50 chance it shows up on A or B. Okay, nothing unexpected then. Now what if the photon takes the lower path? There is still a 50-50 chance it shows up on A or B. From the perspective of the photon, nothing has changed. It doesn't interact with the bomb in any way. So
Why?
the detectors still tell
Wait, what? It doesn't interact? I thought it would cause it to blow up or something.
us nothing about which path the photon took, meaning that it still meets the requirements for quantum superposition. The photon takes both paths.
Quantum superposition is obviously nonsensical. That's a terrible road to go down.
Interferes with itself and shows up on detector A. So if the bomb is a dud, the photon will always 100% of the time show up on
Oh, the bomb is a dud. Okay.
detector A. Now let's try the live bomb. Now this is the game changer.
Wait, it always goes to A? Oh, because that's the way the experiment was set up. Okay.
We place a live bomb in the lower path, and the photon happens to also take the lower path. The photon sensor is working, the bomb absorbs the photon and explodes, so no photon shows up on either detector. Now if the photon takes the upper path, it will either show up on detector A or B. Wait, so the detectors do tell us something here. If no photon is detected, it took the lower path. If the photon shows up on either detector, it took the upper path. Because the detectors tell us which path the photon took, it no longer meets the requirements for quantum superposition and is forced to choose a path. So when the bomb is live, 50% of the time the photon is absorbed and not detected. 25% of the time the photon shows up on detector A, and
I'm lost. I don't even know where she's going now.
25% of the time it shows up on detector B. Now, this last 25% is the real significance of this experiment. So, when no photon is detected, the bomb is live. When a photon is detected on A, it could be either live or a dud, and the experiment needs to be repeated. But when a photon is detected on B, the bomb is live, and we were able to detect this without an explosion. Okay, so there were a few explosions. I mean, a 25% success rate isn't the best in the world, but the idea of a quantum bomb tester is still pretty cool. What did you think about this thought experiment? I would love to hear your thoughts in the comments.
I mean, look, when you don't understand something, and therefore it makes no sense, and you keep going down that road pretending that is reality, you're going to get a weird reality. But you cannot, I mean, obviously we don't live in a weird reality, we live in a very stable reality. So everything you said is wrong, but you agree you don't understand it. When you don't understand something, you cannot, there's no point in continuing down that path. When it doesn't make any sense, you need to stop and think, and yeah, you're gonna get all sorts of really weird stuff, but you're wasting your time. Okay, so we're done with this nonsense. Now let's get back to Zabine. All right, let's see what's going on here. This is this nonsense. Let's see what she says. She contradicts herself. I don't know what's her position on superposition.
I really appreciate the company. Let's look again at that semi-transparent plate because it can teach us something very important. We'll now try to build a simple hidden variables model that explains what happens at that semi-transparent plate, also called a beam splitter. We want to do this with hidden variables, and we want to do it locally, so no action at a distance. The hidden variables are usually called lambda. So we'll say if lambda is 1, then the photon goes that way. If lambda is 3, then it goes the other way. Why 3 and not 2? Because I know what's coming next in detail.
1 second. What? What is she talking about? One second. One second. Okay.
You don't. Now we put 2 mirrors here and here so that the photons don't run off our screen, and another 2 semi-transparent plates there. Okay, so now we have 4.
1 second. I don't know what's going on. Okay, whatever.
4 different paths, each with 25% probability. We'll give those the numbers 1, 2, 3, 4. And now we'll combine these 2 paths by directing both towards the same beam splitter. If our hidden variable explanation was correct, then we should get half of the photons here in detector A and half here in detector B.
I don't understand. I mean, how is this relevant to the hidden variables? What about the hidden variables? Did you say something about the hidden variables? What? 1 second. Good. Let me see. Very nice. Okay.
Plate, also called a beam splitter. We want to do this with hidden variables, and we want to do it locally, so no action at a distance. The hidden variables are usually called lambda. So we'll say if lambda is 1, then the photon goes that way. If lambda is 3, then it goes the other way. Why 3 and not 2? Because I know what's coming next and you don't. Now we put two
I don't get it. Why not 2 or A and B? I don't get it.
mirrors here and here so that the photons don't run off our screen, and another 2 semi-transparent plates there. Okay, so now we have 4 different paths, each with 25% probability. We'll give those the numbers 1, 2, 3, 4. And now we'll
So 1 and 2, 1 and 3 are, I don't know. I guess that's why it's 1 and 3?
combine these 2 paths by directing
Okay, 1 and 3 is up, 2 and 4 is to the right, whatever. Okay.
both towards the same beam splitter. If our hidden variable explanation was correct,
You didn't give a hidden variable explanation. What hidden variable explanation? You just said there is a hidden variable that's controlling 1 and 3. 1, you call this one going up. The vertical you called 1, and this one straight you called 3. I don't know if this is related to this one, comma 3. I don't know. I'm completely confused at this point what you're talking about. You didn't even say that this is 50-50. You just said it's controlled by a hidden variable.
then we should get half of the photons here in detector A and half here in detector B. But this isn't what happens. Indeed, you have probably noticed that this setup is what's called a Mach-Zehnder interferometer. If the paths are the same length, then the photon will always go to detector B.
Does she not understand this experiment? This is by design. It interferes at A destructively, it interferes constructively at B. Does she not know this? What is she talking about? It sounds like she doesn't know this experiment.
You can measure it and all. It's definitely real.
That's the design of the experiment. It sounds like she doesn't understand Mach-Zehnder. It's pretty clear she does not understand Mach-Zehnder. When was this? This is just a year ago. She should have had time to prepare. What do you mean it's real? I don't understand. What do you mean it's real? I don't know what to say. This is the design. Initially, when you run the experiment, I don't know what you get. You might get both A and B, and then you realign, you change the distances until you get a perfect destructive interference at A and a perfect constructive interference at B. Yeah. I don't understand the question. I don't see how this is even, I don't know what she's talking about.
The interference in these detectors is exquisitely sensitive to the length of the paths.
What do you mean exquisitely? There's nothing exquisite. There's nothing exquisite. You just have a micro, I think it's called a micrometer. And the micrometer just, right? Red light is actually huge. A wavelength is half a micron. A micron is huge. A micron is just 1/1000th of a millimeter. A millimeter is huge. You can basically almost see it. You can see it with a normal microscope. You can see a micron with a microscope. So this is half a micron. Imagine taking a millimeter. You can certainly see 1/100th of a millimeter with your eye. Well, that's 10 microns. So half a micron, that's one and a half order of magnitude smaller. Maybe with a good magnifying lens, you should be able to see a micron. Can you see a micron? Anyway, but it's a micrometer. You just need to rotate it a little bit, and you get this correction. It's nothing. It's cheap. There's nothing exquisite about it. It sounds like she never connected this experiment.
Is why one can use this type of interferometer to measure tiny deformations. This is how a gravitational wave interferometer.
No, gravitational waves are much more accurate. I think they're at the femtometer, aren't they? They're much tinier. This is half a micrometer. You need to go to nano, and let's go to a single nano and then a single femto. I think so it's a million times smaller. It's basically what a micrometer to a meter is. That is what a femto to a micron is. So it's another dive, I think, right? The gravitational waves. I don't know if I'm right. Let me check. Gravitational wave. What do you call it? Precision. Designed to detect and measure minute distortions in space-time. In space-time. Yeah, not in space, in space-time. How do you measure time? Known as gravitational waves. I guess they're accurate with time as well. These distortions are produced by violent cosmic events, but what are the exact? The most sensitive gravitational waves are like LIGO, Virgo, employ Michelson interferometry. A laser beam is split and sent down two perpendicular arms, where it bounces off mirrors and returns to the starting point. A passing gravitational wave causes a tiny difference in the arm length, which is measured by the interference pattern. Oh, but it's over a very long distance. But it's still just a laser beam, which means the entire accuracy of a laser beam is the wavelength, which is still half a micrometer. That's all it is. So it's not that accurate. I was led to believe that it's super duper accurate. It's not. There's nothing accurate about it. Wait, what? LIGO initial detection of gravitational waves in 2015 had a signal to noise ratio of approximately 4, indicating a precision of about 10 to the negative 19 meters in measuring distance changes. I see. That is much smaller than the wavelength of a laser, which is half a micrometer, which is negative a micrometer is -6. 10 to the -6 meters is a single micrometer. Half of that is still, well, it's -7. That's all it is. This is -19. That's double is 14, and another 7. Well, it's not triple, but it's 2.5 times smaller than the wavelength. So yeah, because the interference, you can see interference in less than a wavelength. Advanced LIGO is 10 to the negative 20, 10 to the negative, yeah, that's already three times smaller than the wavelength of the laser. Okay, they're just very sensitive to the interference. They're not looking at the wavelength, they're looking at the interference of two waves, which you should be able to notice in much less of a motion of a wavelength, which is good. All right. Okay, yeah. So I guess it's the same technology. It's basically the same accuracy. I have to run to the bathroom.
It works. But how does it work? Well, in quantum mechanics, the photon is described by a wave function, and waves can interfere with themselves.
A wave function is not a wave. Why do you say it's a wave function? The wave function is just the probability of detecting if you look somewhere. It's not the same as a wave. We know it's a wave, but the probability of finding it being a wave function, I don't know if that's even related to it being a wave. I think the wave function, you can use it for macro objects as well, couldn't you? It's just, you flip a coin, what are the chances that it will come tails or heads? You can use the wave function to check, no? It has nothing to do. I don't know enough about the wave function, but I don't know if it's because it's a wave. We know, how do we know it's a wave? Well, we know light is a wave, and we know that a single electron, whatever that means, de Broglie predicted it, that it would behave like a wave, and we tested it, and it did behave like a wave. That's what they say. That's what we know. So I don't know any better than what I'm told. So all elementary particles are waves. That's what they keep telling us. And it makes sense. To me, it makes sense. To me, it's necessary that everything is a wave, ultimately, in the ether. Everything must be a wave in the ether. That's my intuition.
Either constructively or destructively. In quantum mechanics, the photon goes over both paths, and on this output, the wave
It has nothing to do with quantum mechanics. If you believe it's a wave, if the particle is not a particle, but rather it's a wave, then it should be able to go through both paths. If it's a wave in the ether, it should be able to go through both paths. Which is a problem if you also assume that it cannot split, that there is no half of an electron. So how does it do that? That we still don't know.
Interferes destructively with itself, so no signal, and all photons go the other way. But the price you have to pay for this is that if you measure which path the photon went, you need the non-local collapse.
No, you don't. You don't need a non-local collapse. I mean, I don't know. So, okay, I don't know how it all worked until now. So there's no point in continuing the discussion. I don't know what to tell you. What you said up until now is not logical. It's not sensible. I cannot imagine it. So now that you're continuing down the path that I did not understand, I don't know where you're going, and you can say anything you want. You can say that it makes you pizza, and it doesn't make you pizza, and there's no contradiction. You could say anything you want. I don't know. At this point, I don't know what's going on. I'm sorry. What's the point of continuing a discussion about something we all agree we don't understand? What's the point?
Well, in quantum mechanics, the photon is described by a wave function.
Why do you say that? And why do you call it a wave function? Why do they keep calling it a wave function? Is it a wave function? It doesn't Mental Science Asylum says, Nick says, it's a heat equation. So it's heat. It describes the spread of heat or a heat map. I don't know. If it's a heat equation, heat just describes the way he describes it is just the change of states. How it's heat. If it's heat transfer, I don't know. I just don't know. Is it heat transfer? Is that the wave equation? And then it's just different heat transfers.
And waves can interfere with themselves, either constructively or...
Wave cannot interfere with itself. A wave, you can split a wave. A normal wave can be split in two, and then you have two waves, and they can interfere with each other, but then it's two waves. If you're able to split an elementary particle, then it's no longer an elementary particle. I don't know.
Or destructively. In quantum mechanics, the photon goes over both paths, and on this output, the wave interferes destructively with itself, so no signal, and all photons go the other way. But the price you have to pay for this is that if you measure which path the photon went, you need the non-local collapse. How can we...
I don't know. I don't know what she's talking about. I don't know. At this point, I'm confused. I'm baffled by this, by everything.
use hidden variables to get this done locally? Well, no one's ever said that we can't have waves that go two paths in a local hidden variable model. All we need to do is say, if we measure which path the photon goes, then we use these variables, 1, 2, 3, 4, and the photon behaves like a particle. If we measure the interference between the paths, then that's hidden variable number 5. The photon behaves like a wave and goes only into detector B. Problem solved. It's local because the photon goes on one continuous path into the detector where it's measured. For this to work, the value of the hidden variable that determines what the photon does must depend on what you measure. It's called a violation of measurement independence.
I don't know. I never understood this entire segment. I've listened to it many times. I don't know what she's talking about.
So the lesson is, if we want a local hidden variable model that reproduces quantum mechanics correctly, then it needs to violate measurement independence. This finally brings us to Bell's theorem. I'm not going to explain Bell's theorem because you've already watched 20 videos about it and it didn't help. I'll just tell you what it says. Bell's theorem says if you want a local hidden variables model that reproduces quantum...
This is just, it's too confusing. I just don't know. At this point, I just don't know what's going on. This is too much, too many unknowns to have a normal discussion of any type. I don't know. This, I don't know. I don't know.
mechanics correctly, then it needs to violate measurement independence. Isn't that what we just concluded from this little example with the interferometer? Yes, Bell's theorem says the same thing. You see, what happened is that Bell originally just assumed that measurement independence is fulfilled. He then proved that any local hidden variables theory which fulfills this assumption will obey an inequality for the correlations of certain measurement outcomes. It's now called Bell's inequality. Quantum mechanics can violate this inequality. What the Nobel Prize was awarded for is experimentally demonstrating that these inequalities are indeed violated by observed measurement outcomes. This means that either reality respects measurement independence but is not locally causal, or it's locally causal and violates measurement independence. Just logically, it could be a combination of both, but I don't know why you'd want to do that. Since Bell had forgotten about this assumption of measurement independence, he mistakenly thought that demonstrating an experimental violation of his inequality would rule out all local hidden variables models and thereby show that spooky action at a distance is real. Indeed, most physicists still seem to believe this. At this point, you might think Sabine is talking complete rubbish, because if that's right, why doesn't anyone ever mention this? Well, first of all, you don't have to take my word for it. It's all in the published literature and easy to check. In fact, one of the people who pointed out that Bell had forgotten this assumption was John Clauser, who was one of the recipients of the 2022 Nobel Prize. Why physicists refuse to mention it is a very interesting question to which I don't have an answer. My best guess is that they want reality to be weird because they like the mystery. There are several hidden variables models that are local and that reproduce the predictions of quantum mechanics by violating measurement independence. I'll leave you links in the info below.
So there's a few models that reproduce this with local hidden variables. Interesting.
And yes, a violation of measurement independence has also been called superdeterminism, though this term is extremely misleading. I talked about this in an earlier video. In summary, quantum mechanics is not local. What makes it non-local is the collapse of the wave function. The question is whether this non-locality is physically real. If the collapse of the wave function was a physical process, it would be what Einstein called a spooky action at a distance, and reality would be non-local. It has not been shown that this is indeed the case, no matter how many headlines say otherwise. Entanglement is a non-local correlation that can stretch over long distances, but it's not what Einstein meant by action at a distance because there's no action in it. If you're a fan of the many worlds interpretation of quantum mechanics, you probably took issue with some things I said, but this video is already too long, so I'll talk about this some other time. If you want to hear me complain about many worlds, don't forget to subscribe. Yes, I admit there's a lot going on in this video that I only touched on very briefly. What is a wave function? How do you get probabilities out of it? How does interference work, and why?
The problem with these videos is that they pretend to be simple. And by pretending to be simple, you're actually exacerbating the issue of everyone not understanding quantum mechanics. See, if you ask a question and you also say, oh, it's very simple. As you ask it, you say, okay, I'll ask you a simple question. And then you ask a complicated question. You're exacerbating the problem of the question. Questions are difficult enough in general. So when you also say, oh, it's very simple, you're putting pressure and you're adding just a little bit confusion. And when you make these short videos that there's so many questions left unanswered, that you're just exacerbating the problem that you're trying to solve. You're trying to explain quantum mechanics, but you end up sending everyone running away from quantum mechanics. This is the problem. I don't want to say you are the problem, but this is the problem. Let me see a message. What is the message? What is that? Some people keep adding me to all these communities. Oh my God. More communities. Exit. I just want to report all these communities. I don't care. What is this? Welcome to a community. Oh my God. Welcome to another community and another. Oh my God. So I don't know what to say. And then she ends, if you're a fan of the many worlds. That's Sean Carroll. And Sean Carroll, he believes exactly the opposite of everything she said. See, he believes that it's not correlation. So I don't know. Really confusing stuff. So my intuition is that there should be nothing special about quantum mechanics. It should be identical to wave mechanics. Everything should be explainable. It's just wave mechanics. Just like special relativity is explained, all of special relativity should be explained through wave mechanics. The time dilation certainly is explainable, and therefore length contraction should be explainable. I mean, it is, because Einstein already did the work. He just didn't do it relative to a preferred frame of reference. All that ether is, and therefore the fluid is just a preferred frame of reference. That's all it is. So special relativity, as far as I understand, is just wave mechanics. That's simple. General relativity is just, at least the gravitational part is just wave mechanics. That's very simple. That's explainable very easily through the ether. Okay. And then once you assume ether, which you should assume because of Maxwell, but fine, you assume ether, then you cannot really have particles. I cannot see how we can have particles in this universe except for the ether. So then everything becomes wave mechanics in the ether, which is the quantum field. So everything should be really very straightforward. I don't see why we're having any issue with quantum mechanics. So we should be able to just look at every experiment in quantum mechanics and resolve it. It should all be resolvable. I don't see why we're getting into we're getting our panties all tangled in a bunch. I don't see why that keeps happening. It shouldn't be happening.
Why is it important? If you want to understand this in more depth, you can do this with my course on quantum mechanics at brilliant.org.
I just listened to your introduction to your course, and I want to run away from it. You're either a terrible explainer or you don't understand it. Something is wrong. Anyway, I need to run to the bathroom, but I want to continue. But let's take a break. I'll stop here, and we'll come back and continue right after this.